Hello everyone, and welcome to another remote sensing lecture video. And in this video, we're going to build upon our previous discussion talking about the dimensions of remote sensing. In specific, we're going to focus on the second dimension, the spectral dimension. And just like with the spatial dimension, I just want to point out that you'll often see this referred to as spectral resolution. And I want to go through the same sort of process. I want to just give a quick one sentence overview definition, and then we'll build off of that overview definition into a more refined definition and talk our way through some diagrams so that hopefully you have a better understanding of the terminology that's important. So when we talk about spectral dimension or spectral resolution, we're talking about the number of bands and I'm putting "and" in caps here, and I'll even underline that, slide over here a little bit, and the wavelength, and I'm going to use the term sensitivity. Right, that's supposed to say sensitivity of those bands. All right, so we're talking about the number of bands and the wavelength sensitivity of those bands. So I'm saying bands here, again, I'm tying directly back into that remote sensing data structure where we're talking about the different bands, like that Z dimension of the image. And so now let's do what we did before. Let's go ahead and let's give ourselves some space over here. And let's talk about the spectral dimension of remote sensing. Right, the spectral dimension of remote sensing. And again, we're going to write down our definition again. It's both the number of bands and the wavelength sensitivity of those bands. And so the way that I approach the idea of the spectral dimension of remote sensing is I like to start with this idea of the number of bands, right? And again, just to recap, when I say bands, what I mean is the number of bands in that remote sensing data structure, right? That Z-axis of the image. And so I like to think of this as sort of a continuum or a spectrum, if you will. And so we have one end over here. This would be an image that has only one band. And this continues all the way through over here to something that has maybe 100. Let me clean up my handwriting a little bit there. Something that has maybe 100 plus bands. And we have all this space in the middle. So over here in the one band category, we have what's called panchromatic. Right, panchromatic. And panchromatic is one band which is sensitive to all visible wavelengths. And then on the other side over here, when you start having 50, 60, 100 plus bands, right? On this side of the continuum, you have what's called hyperspectral remote sensing, or hyperspectral, HYPERSPECTRAL, hyperspectral. And hyperspectral has, it's kind of hard to put a number on it. I would typically say 15 plus bands. And the key thing with hyperspectral here is they have very actually, let's do very in a different color. Let's do very in red. With very specific wavelengths. And just to sort of recap and tie this into previous content, when I'm saying wavelengths here, I'm talking about that electromagnetic spectrum that we talked about previously, where we used wavelength to define the different regions: red, green, blue, near infrared, gamma, X-ray, right? We use wavelength as that unit of measurement to define those regions. All right, I'm using it again here to specify it. Well, if we have panchromatic, right? If we have one band, if our image has one band that's panchromatic, well, it's taking in information from all the wavelengths in the visible spectrum. So it would go all the way from blue all the way to red, taking all that energy in. Over here on the other side of that, we have hyperspectral, right? We have 15 or more. Typically, you're going to see it be 60 to 150, but 15 or more is a generally decent cutoff for hyperspectral. But the key is that they have very specific wavelengths. So a hyperspectral remote sensor might have a band that only measures or only accepts electromagnetic radiation from, say, 450 to 455 nanometers, right? So it's a very tight, narrow blue band. Right, so we have panchromatic on one side, and we have hyperspectral on the other side. And somewhere in the middle, right, somewhere in the middle here, we have this range in the middle here. We have what's called multispectral. Right, and multispectral is, it's literally just what's it's in the middle, right? It's 2 to 15 bands. Right. Now, the key thing with multispectral here is that you can have broad or narrow band. And we're going to talk about the difference between broad and narrow band here in just a second. But to sort of precursor that, broadband means that it's not very specific in terms of wavelength. Narrow band means that it is a little bit more specific in terms of wavelength. So what I want to do now is I want to talk more and give another diagram showing what I mean when I say broadband, narrowband, very specific wavelengths. What do I mean? What does that look like graphically? So what I want to do is I want to draw a quick graph. And so we're going to have two axes. We're going to have a y-axis, and we're going to have an x-axis. So on the x-axis, this is going to be wavelength. On the y-axis, this is going to be sensitivity. Right? So the higher the sensitivity value, the more that wavelength is going to contribute to the pixel value. Right? And so on the one hand, you have panchromatic, right? So we're going to say that down here, we're going to start this off at 400 nanometers. And we're going to end it over here at 700 nanometers. Okay. So on the one hand, you might have something that looks like this. Right, so this would be panchromatic. This is your panchromatic, right? It's one band and it pulls, has wavelength sensitivity. This has wavelength. This has wavelength sensitivity. Across the visible spectrum. Across the visible spectrum. And that's the panchromatic that we were talking about. So what does it look like if we were to have hyperspectral remote sensing? All right, so let's just draw red, green, and blue. All right, so for hyperspectral remote sensing, it might look something like this. Oop, not quite as straight as I would have liked it to be. Let's see if we can undo that. Or erase it and see if we can't improve our line work here a little bit. Right, so with hyperspectral remote sensing, right, we're talking very, very narrow. So we may have one band that literally just measures, say, 425 nanometers, right? This would be hyperspectral. Right, hyperspectral. And in the green, it might be the same thing. You know, we might just have one very narrow range. It could be, say, this may be 550 nanometers, right? And this could be, say, 625 nanometers. Right, with hyperspectral, it's just a single line because we're measuring 1, 2, maybe three wavelengths. Right, it's very, very specific. So what is that going to look like as opposed to, say, broadband multispectral? All right, so broadband multispectral, on the other hand, it's going to still be in the red region, right? But broadband multispectral is going to pull in, you know, information from a wider wavelength region, right? It's still red, right? It's still in the red region, but it's pulling in a lot more wavelengths. So this would be broadband, right? Broadband, right? Pulls in. I don't use pulls in. It's not used to the term pulls in. Let's say it is sensitive, right? It is sensitive to many wavelengths. Right. Now, how would we compare this then to narrowband? So if hyperspectral is basically a single line measuring 1 to 3 wavelengths, and broadband is measuring a chunk of the region, right? Narrowband sort of splits the difference, right? So narrowband might look something like this. Right, this This right here, this would be narrowband, right? Sensitive to a few wavelengths. All right, so hopefully that makes sense. Panchromatic, right, just to recap, is pulling information in from the entire visible spectrum, right? Hyperspectral, right, that's what this is right here. This is hyperspectral. Right, hyperspectral is sensitive to 1 or 2 wavelengths. Broadband is sensitive to many wavelengths in a given region. And the narrowband is sort of in between. It's sensitive to a few wavelengths. And so what I want you to take away from this is the idea that there are 4 different types of data sets. There's panchromatic, that is the entire visible spectrum in one band. There is the other extreme, which is hyperspectral, where you have bands that are tuned to very, very specific wavelengths, 1 to 3 nanometers wide. And then you have broadband, which is sensitive to a region, say red, green, blue, near infrared. And then you have narrowband, which is kind of in the middle. So just like we did when we talked about hyperspectral remote sensing, actually, let me finish up our definition of hyperspectral here, right? Sensitive to 1 to 3 nanometer, right? 1 to 3 nanometers. So it's very specific, right? But what I want to do is I want to wrap this discussion up, say the same way we wrapped up the idea of spatial resolution. And I want to ask the question, right? I want to ask the question, right? I want to ask the question, right? Why not always use hyperspectral? Right? Because clearly hyperspectral, right? It's got the most specific wavelengths. So why not always use hyperspectral data? Right? Why wouldn't you, just like with spatial resolution, why wouldn't you always go for the highest spatial resolution? Why not always use hyperspectral imagery? And I think it's a lot of the same reasons. And there's really 3 that I want to hit on. Right? The first is cost. Right? It's expensive to build a hyperspectral sensor. And because it's expensive to build a hyperspectral sensor, it's expensive to get hyperspectral imagery. Right? It's not nearly as widely, and because of that, it's not nearly as widely available. Which brings me to the next point, which is availability. Right? It's not everywhere. Right? In current remote sensing capabilities, we have satellites that image every part of the globe almost daily. The problem is 90% of those sensors, actually all of those sensors now, would tend to be narrowband multispectral. So you just can't simply get hyperspectral remote sensing data everywhere, when and where you want it. And I think 3 is probably, whoa. I think 3 is probably the most important. And this is the trade-off. Between spectral resolution trade-off between spectral resolution and data volume. Right, so as a general resolution, as a general principle, right, as you increase your spectral resolution, right, and I'm going to just make this, we're talking about more bands. You increase your data volume. So if what you're doing doesn't need hyperspectral data, you have extra data volume, right? You're taking up extra space on your hard drive, or you're paying for extra space on the cloud for something that you just don't need. Or maybe you do want hyperspectral data, but your computer that you're using just simply can't handle the volume of data. And again, this isn't as big of an issue in modern computers, but it's still an important consideration. Don't use extra data volume when you don't need to, especially if you're paying for it on the cloud. So I know this video in particular can be a little bit dense and a little bit confusing. So I really strongly encourage you to pause, go back, rewatch any parts you're confused about. And as always, please reach out. Thank you.